This is a calculus application that seems appropriate at this point, and it answers the question, what if you're trying to solve an equation and it is not something that you have a formula for? Can you perhaps approximate the roots of the equation? Well, that's a part of something called numerical analysis, and there's many methods out there for approximating roots of equations. Here is one developed by Newton that uses elementary calculus, which is the reason it's mentioned here. So first of all, let's develop the method so you know where it comes from. Here is the idea. The question is, we are looking at a function of one variable equal to 0. This is the equation we want to find a root for, an x value that makes this true. So here is the picture that shows you how Newton thought of this idea. Imagine our curve looks something like this. This is the function here, f of x, in this equation equal to 0. And here is the unknown root. We know there's a root there perhaps, but we don't know what it is, and we want to approximate it somehow. Well, suppose you've been making approximations, and you have some nth approximation at this stage of the game. So maybe you have an xn value, which gives you a point on the curve xn, f of xn, and that is your latest approximation to this root. So xn here is your latest approximation to this root, some distance away. Let us look, using calculus course, we can look at the tangent to the curve at this point. Now the slope of this tangent, as you know, is the derivative at xn, so f prime at xn. We already know how to calculate that. This xn, remember, is an nth guess to r. All right. Well, this line here is an equation, is a tangent line that has an equation. So let's write that down. The equation of this tangent line, we have everything that we need to write it, is going to be y minus the y value, it passes to this y value, f of x sub n, equals the slope, which is this slope, f prime at x sub n, times x minus x sub n. There's the equation of the tangent line. Now notice that the tangent line strikes the x-axis right here, and it seems like it's closer to the root than xn was. That is the heart of Newton's method. He says, perform this operation, find this tangent line, see where it crosses here, whatever point that is, make that the next number, which would be xn sub n, x sub n plus 1 here, the next number in a sequence of approximations that we hope will approach the root. Now, whether or not we actually get there in finite amount of time is irrelevant. As long as these are getting closer and closer, we can stop whenever we feel we're close enough to the root. So, what we need to do is see where this tangent line crosses the x-axis. So when the tangent that we were just talking about at the tangent to the curve at xn, f of xn, when that intersects the x-axis, which of course is the line y equals 0, we have the following. In the original equation for the line, now the y value is 0, so 0 minus f xn is equal to f prime of xn times x minus xn. And we're trying to find out what x value is now being determined by this intersection of the tangent line with the x-axis. So we just solve for x. So let's see here. This is minus f of xn over f prime of xn equals x minus xn. I can solve for x, and I'll put it on the other side. And I'm going to rename it now. Since this is the next number in my sequence, I'm going to rename this as x sub n plus 1, the very next number in my sequence. This now, solving this for x, will be x sub n minus f of x sub n over f prime of x sub n. And this will be true for n equal 1, 2, 3, and so on. And n equal 1 would be the first initial guess, and then all the others would be calculated by this formula. This is often referred to as Newton's method, iterative formula. So this is perfect for putting on a computer and writing software to iterate this. The idea again is you start with an n equal 1, so you have an x1, and where does this one come from? It comes from anywhere. It is a guess. It's your initial guess for the root r. Once you have that, however, you can compute x sub 2 using x sub 1. And once you have x sub 2, you can put it on this side and compute x sub 3 using x sub 2 and so on, and develop a sequence of numbers that you hope will approach the actual value r to any degree of accuracy. So here is the use. As I just mentioned, 1, you want to guess a first approximation, and we call that first approximation x sub 1, to the unknown root r. How do you do this? By any means at your disposal. Perhaps you draw a picture of the graph and you see roughly where it's crossing the x-axis and use that as your guess. Any way will be fine. Then you use Newton's formula to generate a sequence, and that sequence will be x sub 1, the initial value, then x sub 2, which will come right out of the formula, use x sub 2 to get the next one, x sub 3, and so on, up to some x sub n value, and then you can just continue if you like, which, this sequence which, if all goes well, and that's something worth discussing, if all goes well, this should converge to the unknown root r as n grows. Finally, when do you stop this method? See, this produces an infinite sequence of values that you're hoping are getting closer and closer to r. When do you stop? Again, your judgment comes into play. When do you want to stop? When you are within 1/100th of the possible root, or 1/1000th, or 1/1,000,000th. It's all going to be depending on your needs. So stop when you are satisfied that your current r value, current xn value, is approximately equal to r. That will depend on circumstances and your physical needs in a problem. Let's do an example of this. Here's an example, and we'll just do this for a simple polynomial. Approximate a root using Newton's method. Now, Newton's method is really Newton's method for approximating roots to equations. Most people just say Newton's method, but you should understand what it is actually, what its actual full name is. And here's the equation: x cubed plus 3x plus 1 equals 0. Now, unless you happen to have memorized the formulas for solving a cubic, which is doubtful, you'll need to approximate the roots here. So, solution. Well, I need a function. For Newton's method, I need to have a function. The function will always be the left-hand side if this is equal to 0. So the function to be used in Newton's method is f of x equals x cubed plus 3x plus 1. Well, Newton's method also involves the use of the derivative, so let me calculate that while I'm here. This is 3x squared plus 3, and I notice I can factor out a 3, so I'm going to do it. Always make things simple if you can. Now, Newton's formula is a generic formula. With this particular function, you should write out the specific version. So this is the specific version of Newton's formula for this problem, because you're going to use it to calculate. Okay, the specific version of Newton's formula here is going to be what? Well, xn plus 1 will equal xn minus, I'm supposed to put f of xn up here, so that will be x sub n cubed plus 3x sub n plus 1. This is f of x here. And on the bottom, I'm supposed to put the derivative, which is 3x sub n squared plus 1. So here is where the derivative goes. And this is now the specific formula for this specific situation. This is now where I need to start. To begin, I'm going to need to guess an x1. How do I guess it again? By any means I like. If you look at a picture of a graph of this function, perhaps you get an instinct that a good starting place might be something nice and simple. would be x1 equal minus 0.3. So that is the guess we will start with here. Every numerical approximation method always begins with a guess, and then we hope we make the guess better. Then, how do we get x2? Well, we get x2 from x1. So x2 is x1 minus, and I use the Newton's formula, x1 cubed plus 3x1 plus 1, all over 3 times x1 squared plus 1. Now put x1 in here, the minus 0.3, and if you use your calculator, you will see that x2 then becomes approximately minus 0.322324159, and so on. Notice that from x1, remember x1 was equal to minus 0.3, we have repeated one decimal. So this first step has not really improved our approximation very much. We know that this decimal repeats, and so it's probably part of the right answer. We'd like to do better. Well, continue the process. Now you have x2. You can use the iterative formula to get x3. So you're going to get x3, and I won't do all the details here. You can work this out with a calculator. x3 will be approximately minus 0.3221853453546. And notice now that 322 repeats, and will continue to repeat in subsequent iterations. So you've got at least 3 decimals secure in the value of the eventual unknown root r. And if you're happy with 3 decimal place accuracy, you could cut it off here and stop here. So this is 3 decimal place accuracy. And this just continues. And you stop whenever you're happy. That's all that Newton's method is. It's the use of the iterative formula again and again and again, perfectly designed for something to be written into a piece of software. Every method in numerical analysis for approximation has its strengths and its weaknesses. None of them is perfect. So let's talk about the strength and the weaknesses of Newton's method. The first thing to mention is its strength as opposed to other methods. And let me just remind you the formula, the iterative formula, that xn plus 1 is equal to xn minus f of xn over f prime of xn. There's the Newton's formula to keep that in mind. What is the strength here? Well, the strength is that the convergence is very fast. If it converges at all, we'll talk about that in a moment, it has fast convergence. What does that mean? It means you approximately double the number of decimal places with each iteration. So if you only got 1 decimal place with your first iteration to x2, then by the time you get to x3 on average, you should have twice that many, 2. On the next one, you should have probably 4 correct. The next one, 8, and so on. That's very fast convergence on the whole. Now, what are its weaknesses? Well, there are several, and most of them are ones that can be easily repaired, but they should be mentioned. Here, let's mark this as A. The method fails if f prime at xn is 0. Well, here's the formula, and algebraically it's obvious that that fails because that would be division by 0. So that would be algebra saying we have division by 0. But also, you can look at this geometrically, and the geometry says if the derivative is 0, that means the slope of the tangent line is horizontal, which means it's parallel to the x-axis, meaning that the tangent will never strike the x-axis, and so you'll never get to the next x sub n plus 1 member of that sequence of iterations. So the geometry says that the tangent is horizontal, and hence will never strike, and so the method can't continue. So there's 2 reasons why this would fail if the first derivative is 0 at one of the xn's somewhere. All right. It's possible with this method that it may converge to a different root than the one you intended. This is disconcerting, but not a real problem. A different root than you desire. So you may take an x1 value as close to the root that you think you're looking for, and then set up Newton's method and start it to run, and you find out that it starts moving away from that root and converging on another root. That can happen. What else can happen? Well, here's one more. It can fail to converge at all. And it can fail to converge to any root, and it can do this in two different ways. One way, it can go to infinity. It can just keep getting further and further out in one direction or the other. So infinity, I guess I should say, or minus infinity. Or it could oscillate, which means it looks like things are going well, but all of a sudden you come up with an iterate which is the same as one came up previously. And then it starts cycling through that collection of iterates and never goes anywhere. Here are some cases for you to try. I won't work out all these details, but if you try these 5 cases, you'll see how all of these various failures can occur. And it's fun to do that, whether you do it by picture or with a computer screen or a calculator screen. First, consider f of x equals sine x. Nice function. The root we're interested in, that we're trying to find, is the one at 0. And as your first approximation, take x1 equal pi over 2 minus 0.02. The second one, which is another one that will give you a problem, take the same function, the same root of interest. This time start with x1 equal pi over 2. I think you'll guess what happens there immediately. Here's another function to try. Try x cubed minus x. Again, the root is 0. And let's start with x1 equal 1 over the square root of 5. This one's particularly nice because this is an example of one that's going to oscillate. You need to see it to believe it. Here's a fourth example for you. F of x equals square root of x, which is only defined for positive x's and 0, of course. Here's r equals 0. We want to find that. Start with x equal 1, x1 equal 1. Finally, take x times e to the minus x as your function, r equals 0, the root you're looking for, and let x1 equal 2. In every one of these, starting with these x1s, let Newton's method run, and it won't have to run very long before you see what's happening. Either you will get no convergence, going to infinity, or oscillating, or you'll get something that is undefined for some reason, or something else might happen. These are all fun to look at, so go ahead and do that. The title of this section is the mean value theorem for derivatives. But it's also about a sequence of mathematical theorems that show you that the calculus is well-founded. It's not just a collection of techniques. So I think you'll enjoy this, where we do a couple of proofs. The first thing we'll look at is a special case of the mean value theorem. That's Rolle's theorem. And all of these theorems are very, very straightforward to explain. Here's the idea behind Rolle's theorem. Imagine you have a function that's continuous and differentiable. So it has all the nice properties we've seen before. And maybe it does something like this. So at a point A here and a point B here, the function is definitely 0. It may be 0 elsewhere, but it's definitely 0 at the A and the B. Now notice, the line between A and B is the x-axis, and that's a horizontal line. It has slope 0. Up here, there seems to be a horizontal tangent line here. So this seems to be a horizontal tangent. And of course that means it's a 0 derivative of the function at that point. There doesn't seem to be any way that I can draw a continuous function that has derivative everywhere and go from A to B without at some point traveling in this direction, having a horizontal tangent. Not only do I have this one here, I have a second one in this case. But even if I had a smaller version where I had A and B here, and I tried to get from A to B with a continuous function, see, there's no way to get there without passing through a point where the tangent is horizontal and therefore parallel to the x-axis. That's all that Rolle's theorem recognizes and proves, that this horizontal tangent in this case must occur at some point. So here's Rolle's theorem. And it goes like this. It starts off with the conditions I've already mentioned. If f is continuous, and it's continuous on our closed interval, and we know that f is differentiable, that is, has a derivative on the open part of the interval, as we've done before. We'll talk about this hypothesis in a minute. And one more thing, f at the left endpoint is 0, and f at the right endpoint is 0. Now we will generalize this theorem in just a moment to the full mean value theorem, in which we don't have this constriction. However, for here, this restriction will be in place. So the function touches down at 0 at the a and the b. Then what do you conclude from this? Well, you conclude what we noticed up here, that there is at least one, there may be more than one, but there's at least one point C in the open interval AB such that the derivative at C is equal to 0, which means the tangent line above C or below C is going to have a derivative of 0 and therefore is going to be a horizontal tangent. This now, just to replace it by a phrase that will be useful in just a moment, this is the slope of the secant line between 2 points on the picture. Up here, this point here, of course, has coordinates a0, and this point here, of course, has coordinates b0. So this would be the secant line between them, the slope of the secant line between a0 and b0. So that's what this 0 right here represents. The left-hand side, of course, is the derivative, which is the slope of the tangent line. And let me mention one other thing before I leave this. It really is essential that the function has a derivative everywhere, because it's easy to draw a picture that shows that this hypothesis is necessary. This hypothesis is needed. For example, you might have a picture where you have something like the absolute value function. Maybe here's a and here's b, so there's definitely 0 there. But notice that right here there's no derivative, and nowhere else is there a horizontal tangent line. So this theorem would not be true if we don't have this hypothesis that the function's differentiable everywhere on the open interval. So we do need that. All right, let's go ahead and look at a proof of this theorem now. So here's the proof of Rolle's theorem that we just saw. And as I mentioned, this is a nice example of mathematical reasoning, so you want to pay attention throughout this entire section. Rolle's theorem. Well, let's break this up into cases. Let's suppose we have a really easy function, f of x equals 0 for all x in the open interval ab. So f is this constant function. Well, if it's a constant function, its derivative is 0 for all the points in here. In other words, we can say then f prime of c is going to be 0, because the derivative of a constant function is always 0, for all c in the open interval AB. And the c can be any point in there. Derivative of a constant function is 0, because what's the graph of a constant function? It's a horizontal line. Okay, well that takes care of the case where the whole function is 0. Let's suppose that it's not 0 somewhere. And for this first case, part 2 here, let us suppose that f of x is greater than 0 somewhere for some point in the open interval AB. Now, since f is continuous on this closed interval AB, we have a theorem we've seen before called the extreme value theorem, which says continuous function on a closed interval is guaranteed to have a global max and a global min. In this case, since this point, whatever this point is, has a functional value greater than 0, and we have other points below it, we certainly are going to have a global max here. Maybe this point here that gave us this functional value greater than 0 is the global max, maybe not, but there at least is going to be one. So we can say that the extreme value theorem guarantees, implies, that f has a global max. And it will have a global max on that closed interval. Now we can actually do better than that. We know it's not going to be at the endpoints, because at the endpoints the function is 0, remember? And that somewhere in between the function's non-zero. So the global max is not only on here, in fact, on the open interval. All right. Now, if it's going to be on the open interval, and we recall since f is differentiable on that open interval, then the only way that a function can have a global max is, and it's not going to occur at an endpoint, is if it occurs at a critical point. Well, critical points are of what kind? They can either be places where the derivative doesn't exist, which won't happen here, or where the derivative is 0. So since f is differentiable on AB, there must be a critical point, C in AB, where f prime of C is equal to 0, because if the derivative does exist, it must be a critical point that's in fact a stationary point, and so we must have a point here where the derivative is 0. But wait, that's what we were trying to do. Notice we had that in this first case. Now it's occurred in the second case, so we are done as far as this theorem goes. Part 3, this is the f of x less than 0 case. This is similar. It's an argument exactly the same as this argument, except that you're below 0 instead of above 0, so I won't repeat this argument. But now you have a pretty good sense, I hope, of why Rolle's theorem is true, and the fact that it actually derives from the extreme value theorem, which is very nice. Now, the full mean value theorem on derivatives. I call this the full mean value theorem for derivatives or on derivatives because we'll be seeing a mean value theorem later for integrals, and we want to keep these separate. Here's the idea. It is an extension of the idea of what happened with Rolle's theorem. Imagine we have this situation. Instead of having a function which touches down at 0 above a here and say b here, let us suppose we have a function that doesn't. That is, there are going to be just points here of some kind, a, f of a, and this of course will be the function f of x, and then the point down over here will be b, f of b, and they're not necessarily here on the x-axis. But the argument will be the same. Connect these 2 points here and call that a secant line. That line would have been the x-axis in Rolle's theorem because these 2 points would have been down here at the origin. Now, what the mean value theorem says is if you connect these 2 points like this, and then you look around at the curve, it's clear that there has to be somewhere, there's a point, looks like, where the tangent line is perpendicular or parallel to this line. And the tangent line here is parallel to this secant line. There has to be at least one place. There's no way to get from this point to this point without at some point passing through a point where the tangent line is parallel to the secant line. Another way to say that is there's no way to get from here to there traveling along this curve without at some point being headed in exactly the direction you're trying to get to from A to B. So this is a way of describing what the mean value theorem says. Let's go ahead and mark a few things here. There's A and there's B. And here's a point up here, which of course in the theorem we'll refer to as C. And the theorem will say there's at least one C for which this happens. The tangent line here, this is the tangent, is parallel to the secant line. But in this picture, of course, there are 2. Now let's mark a couple of other things on here. This tangent up here has slope. The tangent slope is going to be f prime at C. It's the point C. Here's the function f, and the derivative, as we know, gives the slope of the tangent line. What's the slope of this secant line? Well, the slope of the secant line, since we have 2 points on the secant line, AF of A and BF of B, is going to be the difference of the y's over the difference of the x's. So the secant slope is going to be f of B minus f of A, the difference of the y's, over the difference of the x's. So now what we're saying in the theorem is that the secant slope, this number here, and the tangent slope, this number here, will have to be equal for some value C somewhere. So let me write that down here at the bottom. At least one tangent must be parallel to the secant somewhere in that interval. It is visually obvious that this has to happen. Now let's prove it rigorously using mathematics. First, let's state it. This is the mean value theorem, and I will say, remember, for derivatives, just to remind you that there's another mean value theorem later. So the mean value theorem for derivatives, and it starts with the same conditions as for Rolle's theorem. If f is continuous on the closed interval AB, as before. F is differentiable, that is to say it has a derivative on the open interval AB. Now there is no statement about f of a and f of b equals 0, as we did with Rolle's theorem. There's no such statement, no such limitation here. We go immediately to the conclusion. There is at least one point, which we'll call C again, in the open interval AB, such that the slope of the tangent line, that's what f prime of C represents, the slope of the tangent line on the curve above or below C is equal to the slope of the secant line connecting AF of A to BF of B. And that's what this slope is here. So to write it out again, this is the tangent slope at the point C. That's what this represents on this side. And over here, this represents the secant slope between the 2 points I mentioned, AF of A and BF of B. So we have a tangent slope equal a secant slope. Don't just think of this as a formula. Think of it as a tangent slope equal to a secant slope. And remember, there are conditions here that have to be met before you get this result. Now, where does the mean come into this? Well, the tangent slope at C says that this is, in some sense, the mean derivative. Or, if you like the word, you can use the word average derivative. Of all the derivatives, this is the mean or the average because it has the same value as the slope of the secant line between these 2 points. Now, having stated this theorem, let's see if we can prove it. And as you might expect, we're going to use Rolle's theorem. That's the reason we did it first. So proof of the mean value theorem, and now I'll start abbreviating it, the MVT, for derivatives. All right. Well, what we're going to do is an argument that involves using the secant line formula. So let's write down, or equation rather, let's write down the equation for the secant line. Well, we know it passes through 2 points, AF of A and BF of B, and we know what its slope is. So I can take either point and the slope and write down the equation of the line. So let me take the first point. Y minus f of A is equal to, here's that slope, f of B minus f of A over B minus A, times x minus the x value of the point AF of A. And let me solve for y here. So this will now be a function thoroughly in terms of x. This will be f of B minus f of A, repeating all of this here, times x minus A plus, and I'm bringing the f of A over. So here is the function that represents the height of the secant line at any point x. So if we look at the picture we are now working with, we have some sort of a curve like this, say. Here's A, maybe this is B, and we're connecting up these 2 points like so. And we're asking ourselves, where is there a point here where there's a tangent line parallel to this? Now, before we get to that, this is the secant line, and we now have a formula that tells me how far the secant line is above the x-axis. I also have a formula that tells me how far the f function is above the x-axis. That's just f of x. The difference of the two, notice, at this point and this, because they intersect, the difference is 0. And at this point, it's also 0 where they intersect. The difference then has different values in between. So the difference function itself is a function that's 0 at the 2 endpoints and has various values in between, which means Rolle's theorem will apply to that function. So we'll let v be that function, which will be, just like I described it, the height of f minus the height of the secant line. That means v now is a function of x, and it's equal to the height of f, of course, is just f of x, that's what f of x means, minus the height of the secant line, which is this value here. So I have, rewriting this yet again, f of b minus f of a over b minus a, x minus a plus f of a. So this is the function that is the difference of the two heights. And this function, we know, by looking at the picture, is 0 at the 2 ends, and I'll write that in a minute. Let's first note that since f is continuous, on the closed interval AB, so is v of x. Why? Because f of x is continuous, and what's this? This is just a line. So it's another continuous function. The difference of two continuous functions is continuous. So we have a continuous function on a closed interval. And observe one other thing, as I mentioned, that if you calculate v at a, let's see what happens. If I put a in here, I get f of a. What happens up here? This doesn't change, it's a constant, but a minus a is 0, so this whole first expression goes away. And then I have f of a minus f of a, and I have 0. So v of a is 0. Also, we can check that v of b is likewise 0. If you put b in here, you get f of b. In here, this doesn't change again. You get b minus a. What happens? The b minus a cancels with this. So now you have f of b minus f of a plus f of a, so the f of a's are gone. And now we have f of b minus f of b, and that's 0. So v of b is also 0. In short, v now is a function that satisfies Rolle's theorem. So v satisfies Rolle's theorem, or more properly, the hypotheses of Rolle's theorem, and therefore the conclusion follows. Meaning, there is a number c in the open interval AB with the derivative of this function at c being equal to 0. So v prime of c is equal to 0. Rolle's theorem gives us that. But wait a minute. I know how to calculate v prime, so let's do that. But v prime of x, if I go through and run the derivative through the function, I get f prime of x for the first part minus the second part is just going to give me f of b minus f of a over b minus a. That's what happens whenever you take the derivative of a line. You just get the slope. So that means this is the derivative. So that means if I have b prime of c equal to 0 on the left here, then on the right that means f prime of c minus this constant, f of b minus f of a over b minus a, must also equal to 0 over here. Well, that means f prime of c and this constant must be the same. That is to say, f prime of c equals this constant f of b minus f of a over b minus a, which is exactly what we were trying to do. So we're done. That is the proof of the mean value theorem. It uses Rolle's theorem in an essential way to get this result that says the slope of the tangent line somewhere at some point c equals the slope of the secant line, which you can write out right at the beginning of your problem. Now let me give you another interpretation before we do any problems here. And this one's very nice. This is another interpretation of the mean value theorem for derivatives. And this takes into account things that you know from your experience, I hope. If, let's suppose s of t is a position function, then if I compute s prime of c and set it equal to s of b minus s of a over b minus a, which is exactly what the mean value theorem for derivatives says, in this case, since s is a position function, s prime of c is the velocity of that position function. So what this is the velocity, or if you like, the instantaneous velocity at time c. So at this time c, which is somewhere between a and b, which now represent times, the velocity at time c has this value. And on this side, what is this? This is the difference of the distances, so the positions, over the difference of times. That's the average velocity. This is the average velocity over the time interval a to b. So this was the instantaneous velocity, this is the average velocity. So for example, this says, just to give you a nice visualization, if the average velocity for your trip, and suppose you take a car trip, your average velocity for your trip is 40 miles per hour, then that means automatically that somewhere during the trip, at some time, you had to be going 40 miles an hour. At some time during the trip, you had to be going exactly 40 miles per hour. That's what the mean value theorem says in terms of velocity. If you go from point A to point B and you figure out that your average velocity is 40 miles an hour, then sometime during that period you had to be going 40 miles an hour. And there's a nice story about how highway patrolmen can tell whether you were speeding by figuring out the time you entered a turnpike and the time you left, and then from that figuring out your average velocity. And if your average velocity exceeds the speed limit, at some time during there you had to be going at that speed to have. Now let's finally do an example. Find, and this is a simple example using algebra, but this is worth doing. Find all the c values that satisfy the mean value theorem, or the MVT for derivatives, for the following function. This will be the function f of x equals the square root of x minus 1, and I'll go ahead and rewrite it for convenience as x minus 1 to the 1/2, on the closed interval of time, if you like, 1 to 3. Now it doesn't have to be time, but that was the example we were just looking at. Solution. First of all, let's note that f is continuous on its natural domain, and its natural domain is what? Well, it's all the numbers from 1 to infinity. If you check this out, this is 0 when x is equal to 1, and then larger numbers for x are allowable. Other numbers would make this negative, and so the square root would not exist. So the f is continuous on its natural domain, hence it's continuous on a smaller part of it, on 1, 2, 3. So we have continuity. We have to find the conditions that the mean value theorem must fulfill. And we have those hypotheses, and the function here must satisfy those before we can draw the mean value theorem conclusion. F is continuous on its natural domain, so it's continuous on the closed interval. Let us note here, and we'll use these later, that f of a is equal to f of 1, because a is equal to 1, and that's just 0 here. You put 1 in here, you get 0. And f of b is f of 3, and 3 minus 1 gives me 2, so we have square root of 2. Let's also note that f has a derivative. This is a well-known function after all. Has a derivative on the open interval from 1 to infinity, hence on the smaller interval 1 to 3, open. In fact, we can write down what that derivative is since we're going to use it. The derivative of f, here's the function f up here, would be 1/2 x minus 1 to the minus 1/2, and so we can rewrite it as 1 over 2 square root of x minus 1. So the upshot is the mean value theorem hypotheses are met, and therefore the mean value theorem conclusion follows. Meaning, and here's that conclusion, there is a c value in the open interval 1, 3 such that f prime of c is equal to f of b minus f of a over b minus a, using the letters of the theorem. Now here the derivative is this. If I evaluate it at c, I get 1 over 2 square root of c minus 1 must equal, and f of b was square root of 2, f of a was 0, and then b minus a was 3 minus 1. So we want to solve for all the c's that make this true. That'll take us to the next page. So what we had was 1 over 2 square root of c minus 1. The right-hand side simplifies to the square root of 2 over 2. I will flip both sides over. So 2 square root of c minus 1 is 2 over square root of 2. Divide out the 2. Square root of c minus 1 is 1 over the square root of 2. Square both sides. I have c minus 1 is 1/2. So c, therefore, is 3/2. And 3/2 is definitely in this interval 1, 3. So that is the one and only value of c where there will be a tangent line which is parallel to the secant line. And if you want, you can graph this. It's always nice to see that this really says what you think it should say. And here is what the function looks like. The square root of x minus 1 function looks something like this, starting here at 1. And if you go over to 3, this is the secant line passing through this point here and this point here. And the tangent line ought to be visually somewhere over here, the one that is parallel to the secant line. And if we come down here, that turns out to be roughly at 3/2 or 1.5. So this seems to be right. And again, the point is that the slopes of these two lines are equal. The slope of the secant line, which you can build at the very beginning of the graph, and the slope of this tangent line, which you discover according to the mean value theorem, because this is the c value that is guaranteed to exist. As part of the sequence of theorems I promised you earlier, now we'll look at some direct consequences of this mean value theorem. And there will be two that we look at. Each of them is a theorem. The first one is actually a theorem we've seen before, but we've never proved. So we'll prove part of this here using the mean value theorem, so you show that it really has a basis in proof. Recall, and this is one that we previously did not prove, so previously not proven. Here's the theorem. Let us suppose we start with a function f, and that function f is continuous on a closed interval ab, and differentiable, f is differentiable on the open part of the interval. And you should recognize those as the conditions required for the mean value theorem to hold. Then this theorem that we had earlier was that if you know that the first derivative is positive, greater than 0, x an interval ab, then that implies that the function is increasing. The original function is increasing on the closed interval ab. So this was the theorem we used to find out where a function was increasing and decreasing. We did it by looking at the first derivative. The first derivative being negative for all x in AB, then implied that f was decreasing, as you remember, on AB. And then the third case, which was the easiest of all, if the first derivative is 0 for all x in AB, that implies that the function is constant on AB. And this one we could actually check easily without the mean value theorem. So we actually know this final result without having to use the mean value theorem. But the first two require it, and now I'm going to prove part A to show you how it's used. So this is the proof of part A only. And part B, of course, is similar, so it's not anything new. All right, I need to show that given that the first derivative is positive on the whole interval, open interval AB, then the original function is increasing. So I want to show that the original function is increasing on that interval. So let's pick 2 points. Let x1, x2 be 2 points in the closed interval AB with x1 less than x2. So that's going to mean that x1, or x2 rather, minus x1 is greater than 0. If you take the difference, the bigger minus the smaller, of course that's greater than 0. So I want to show that the function is increasing, which means I want to show that f of x1 is less than f of x2. That would mean that the function is going up, as we would hope it would be. So let's write that down. We must show that f of x1 is in fact less than f of x2 as we go from left to right. Now, since the mean value theorem for derivatives, that set of hypotheses hold on the closed interval AB, and that of course is what was stated in the theorem, then they also hold on anything smaller. So they also hold on the interval from x1 to x2, the closed interval x1 and x2. So, by the mean value theorem, there is a point C in the open interval x1 to x2 such that the mean value theorem formula or equation holds, f prime of c, the derivative at c, that point c that was discovered here, is equal to the slope of the secant line, f of x2 minus f of x1 over x2 minus x1. Now, if I clean this up a bit, I bring the x2 minus x1 to the other side, and then rewrite this in the other order. I have f of x2 minus f of x1 must equal f prime of c times x2 minus x1. Now, let's remember a few things here. First of all, x2 minus x1 here is positive. Also, remember we assumed that the first derivative was positive on the entire open interval. So that means this whole side here is positive. That is to say, it is greater than 0, which means the left-hand side is greater than 0. But then that means that f of x2 is greater than f of x1. And that's exactly what we were trying to do. We were trying to show that f of x1 is the smaller of the two, and now we have done that. And where was the mean value theorem used? It was used right here in order to get this statement. So the mean value theorem was essential to this and proves that previous theorem. So this is the first of the two consequences. Let us look at the second consequence. The second consequence is called the constant difference theorem. And this answers a natural question. What if you have two functions and they have exactly the same derivative? What does that say about the original functions? Turns out it says that they're almost the same thing. In fact, the only difference between them can be a constant. And this is a new theorem. So the other one was an old theorem. This is a brand new theorem for us. If f and g are differentiable on some interval I, and f prime of x equals g prime of x, so the derivatives of the two functions are exactly the same for all values of x in this interval I, then it turns out that for all x in that interval I, the difference f of x minus g of x of the original functions before you took their derivatives equals k, some constant. And that's the worst thing that can happen. And you can write this another way. Sometimes people write it as one of the functions is equal to the other function, g of x, f of x is equal to g of x plus k. That's another way to write this. And people often say two functions with the same derivative, as we have in the hypotheses here, differ at most by a constant. So this is the sentence that you will hear people say, and this is how this is used. So this is very handy because in practice what happens is sometimes you have the derivatives in front of you, but you don't know the original function. And finding the original function could even be difficult. But if you know the two functions have the same derivative, the worst case scenario is that one of them is equal to the other plus some constant which you may or may not know. So let me show the proof of this. This will use all the material that we've had before. Let's suppose x1 and x2, and let's suppose that they are different in the interval I. Say, since they're different, one of them is less than the other. Let's just suppose it's x1 is less than x2. Now, since this is going to call upon another theorem that we know, since f and g are differentiable, they have a derivative in I, then by a theorem that we had before, if they're differentiable, they're automatically continuous. Differentiability at a point implies continuity at a point. Since f and g are differentiable in I, then f and g are continuous on I. So they're continuous. Now we're building up the sequence of hypotheses we need. So that means f and g are differentiable on a smaller interval than I, the interval going from just x1 to x2, the open interval, and they are continuous on the closed interval from x1 to x2 because these intervals are contained in I, and they have these properties on the larger interval. The same holds true for the difference of these two functions, which we'll call big F of x temporarily, little f of x minus little g of x. If both of these functions are differentiable and continuous in this way, then their difference is also. Now, suppose we take the derivative of this function big F of x. Well, that is going to be little f prime of x minus g prime of x. But these two, remember, we assumed were equal. So the difference must be 0. So this uses our hypothesis here that the two derivatives are equal. So we have to use the hypothesis somewhere, and this is where it's used. That means this function big F has a derivative equal to 0. By the previous consequence of the mean value theorem, we know that if a function has a derivative equal to 0, then the function big F of x must be equal to k, some constant, where it is defined. And it's defined here on the interval from x1 to x2. So that means the original function f of x minus g of x, which is what big F of x is after all, must be equal to a constant at both x1 and x2, because it's true on the entire interval, so it's true at both of these points. So that means this is constant at x1 and x2. But wait a minute. x1 and x2 were different, but they were arbitrary. There was no choice as to what these are. They're just any old points that happen to be different in I, which means f of x minus g of x must equal this constant not only at x1 and x2, but everywhere. Since x1 and x2 are arbitrary, they were arbitrary choices in I, f of x must then equal g of x plus k, just putting the g of x on the other side again, for all values of x in I. Not just x1, x2, or the numbers in between, but every value of x. And that's exactly what the theorem said. So you see, we use this well-known theorem that differentiability implies continuity, and then we use the previous theorem, the previous direct consequence of the mean value theorem, to get this result. So now you've seen some proofs. I hope you've enjoyed seeing the underpinnings of some of the calculus. Here's just a brief overview of what we've seen in the way of theorems and deductions. We had the extreme value theorem from a previous lecture, which we did not prove. To prove that would take us outside the bounds of this course. But starting there, we proved that Rolle's theorem follows. And once we had Rolle's theorem, we proved that the mean value theorem for derivatives follows using standard mathematical proof techniques. And then from that, we got the consequence, and I didn't give it really a name. This is where we use f prime to tell whether f is increasing or decreasing. That's just a quick description of it. And then with another theorem that we had from before, that differentiability implies continuity at a point. Those two together allowed us to prove this last theorem, which was the constant difference theorem. So this is how this all hangs together mathematically. And it's nice to see that this is all happening along the way. That calculus is not just a collection of techniques. There's an actual nice, tightly organized theory behind it. And all of these results, of course, we will use in various ways as we continue through this course. Now for a couple of exercises. Here's the first one. Imagine a car travels 4 miles along a straight road in, say, 5 minutes. Show that the speedometer of the car reads exactly 48 miles per hour at least once during the trip. At least once during the trip. Try it out. this problem is stated, we went 4 miles in 5 minutes. So if we had miles per minute, this would be 4 miles in 5 minutes. Well, that's a little bit awkward because our result was we're supposed to compare this to 48 miles per hour. So let's put this in miles per hour. To do that, I multiply the top and bottom by 12. That will give me 48 miles per 60 minutes, which is 48 miles per hour. Now, what have I just calculated here? This is a calculation, miles per minute, or miles per hour in the end. This is a calculation of average velocity. So that is the average velocity of this car over this period of 5 minutes. By the mean value theorem for derivatives, the average velocity, which is the slope of the secant line of the position function, the average velocity must be, this average velocity must equal the instantaneous velocity, or as we now say, just the velocity, at some point between 0 and 5 minutes. So, 48 miles per hour must appear on the speedometer. Sometime during that 5 minutes. That's all there is to that. So really this was just a calculation of average velocity and then quoting the mean value theorem to say that the speedometer must have that 48 miles per hour appear. Here is a second problem for you. Use the fact that, and I'm just going to give you a derivative here just to save you a little trouble. The derivative of x times the log of the quantity 2 minus x is the log of 2 minus x over 2 minus x. Use that fact somewhere in your result to show that the equation x equals 2 minus x times the log of 2 minus x has at least one solution in the open interval from 0 to 1. So that one is going to give you a little bit of a challenge. Give that one a try. Here's the equation we were given. X equals 2 minus x, quantity times log of 2 minus x. Now notice that this could be rewritten as x over 2 minus x equals the log of 2 minus x. Or if we solve for this in terms of 0, this is the log of 2 minus x over 2 minus x. So that's interesting. That connects us up to the derivative we were given. Here's what we need to do. We must find an x value that makes this true, meaning this equation true. We're trying to find a solution to this equation, so we want to find an x value that makes this equation, which is equivalent to the first one, true. Here's how we can go about doing it. Let f of x be x times log of 2 minus x. Now this f function is continuous on the closed interval 0, 1, and certainly it's differentiable on the open interval 0, 1. And let us note that if you compute f of 0, you get 0 times log 2, which is 0. And if you compute f of 1, the other endpoint, that's 1 times log 1, but log 1 is 0, so that's also 0. So the mean value theorem for derivatives applies. And that's because it's continuous on the closed interval and differentiable on the open interval. Meaning, we get the conclusion, there is a c value in the open interval 0, 1 such that f prime of c is equal to f of 1 minus f of 0 over 1 minus 0. But we were given this derivative because this function here we were given the derivative of. So we were given the fact that f prime of c here is equal to the log of 2 minus, putting c in there for x, minus c over 2 minus c. And then f of 1 minus f of 0 is 0 minus 0 over 1. In other words, we have found a value of c. This value of c sends this to 0. And this is the value of c, satisfies our requirements. So we're done with that problem. I hope you got that.